Welcome, everybody. Learning as a hobby here. I want to finish up chapter 1 in the Taylor book today in this video. Well, I still have to do the exercises, but I'm going to go over the section 1.7 summary in this video, which is the last section in chapter 1. And it's basically a continuation of 1.6, where we went over Newton's third law. Now we're going to do Newton's third law, but in polar coordinates. So let me bring up my chapter summary. All right, here it is. Just move some things out of the way. All right, so this is my summary for section 1.7. Like I said, it's on two-dimensional polar coordinates. Just to refresh your memory on the difference between polar and Cartesian coordinates. Cartesian coordinates, to pick out a point in the plane, we pick two fixed axes that we call the x-axis and the y-axis, and we label them with a number scale on both, and they intersect at the origin, which has coordinates 0, 0. And then we can pick out points by taking the intersection of a vertical line and a horizontal line, and the point on the horizontal axis and the vertical axis where those lines cross will be the coordinates for that point. We always list the x coordinate first and the y coordinate second. So you guys, if you've done any math, you recognize this. This is Cartesian or rectangular coordinates. Excuse me. But we can have there are many types of nonlinear coordinate systems. One important one is called polar coordinates. And for polar coordinates, instead of picking out a point by taking the intersection of two lines, now we have the intersection of a circle of radius r centered at what's called the pole, which we're labeling here as O, and a ray that emanates from the pole and makes a certain angle, which we're calling phi, with the what's called the polar axis. All right. So if we take the intersection of that circle with that ray, then we can write down the coordinates of that point. It has coordinates r comma phi. And I should make one little note here about notation. Apparently in physics, for the polar angle, they use phi for the polar angle, whereas in mathematics they use theta, which isn't really too confusing here. But once we go up to three-dimensional coordinate systems, if you're looking at like cylindrical coordinates or actually, it wouldn't be confusing in cylindrical coordinates, but if you get to spherical coordinates, it can be a bit confusing because the convention in mathematics is to use theta for the polar angle and phi for the azimuthal angle, whereas in physics it's the complete opposite. They use phi for the polar angle and theta for the azimuthal angle. So just a note there, something that to be careful about. So I'll be following the physics convention, obviously, since this is a physics class. So this is the polar system here. All right, we can go back and forth between polar and Cartesian coordinates using some transformations, which we have written here. So if you know the polar coordinates of a point r phi, then you can figure out the equivalent Cartesian coordinates by using the first batch of formulas there. X is equal to r cosine phi and y is equal to r sine phi. Or if you know the Cartesian coordinates, then you can find the one representation of the polar coordinates. There's actually an infinite number of representations for a single point in single geometric point in polar coordinates because of periodicity. So the formulas that he gives in the book are these two: r equals square root x squared plus y squared, phi equals arc tan y over x. Now I don't like this system of transformations for polar, going from Cartesian to polar, but this is the ones that he gives. I prefer the second batch that I have written here for reasons that I'll explain in a second, but he also has an exercise where he elaborates on the problems with the transformations that he gives here. So, but so I prefer these: r squared equals x squared plus y squared, and tan phi equals y over x. And the reason for that is r can be positive or negative in polar coordinates. So here, this is in the first batch of transformations, this is specifying that r is positive or 0. And also arctan of y over x can't give you the quadrantal angles pi over 2 or 3 pi over 2, or coterminal angles with it, nor can it give you any angles in quadrant 2 or 3, because the range of the arctangent, if you remember from trigonometry, is restricted to negative pi over 2 to pi over 2, not inclusive. So I prefer to use this transformation here, tan phi equals y over x, because then you can figure out how to adjust the angle phi to give you what you want. If it's in angle 2 or sorry, if it's in quadrant 2 or quadrant 3, you can adjust by a factor of pi or minus pi. So like I said, there's actually a problem in the exercise set that deals with that, so we'll talk more about that when we do the exercises. Okay. So to define what we mean by the unit vectors in the polar coordinate system, he reminds us what we mean by the unit vectors in the Cartesian coordinate system, and we'll use a similar method for just defining those unit vectors in polar coordinates. So x hat is the unit vector in the direction of increasing x when y is fixed, which you can see in the picture down here. So if r is the position vector, then we can put the unit vector in the x direction, x hat, with its base at the head of r, and that red vector there, that horizontal red vector, is the unit vector x hat. Right? And similarly, y hat is the unit vector in the direction of increasing y when x is fixed. So again, I have the unit vector y hat drawn here in the picture. Something important to notice here, which I did mention in the last video that I made for section 1.6, but I'll say it again. No matter what r is, x and y always point in the same direction, meaning they're not functions, or they're constant functions with respect to time. So if you differentiate them, the derivatives go to 0, which has the effect of making the time derivative of the position vector relatively simple in Cartesian coordinates. You just take the derivative of the x coordinate with respect to time times x hat plus the derivative of the y coordinate with respect to time times y hat. And, you just keep going on like that for higher and higher derivatives. So that aspect of Cartesian coordinates is nice. All right, and then here we make the definition of r hat and phi hat. So r hat is the unit vector that points in the direction of increasing r when phi is fixed. And again, I have that drawn in the picture here. So if r is the position vector, then the red vector that I have here pointing in the same direction as r is the unit vector r hat. So it has length 1 and it points in the same direction as r. And just to make a note, r hat is particularly easy to find if you know what the position vector is, because you just take the position vector and divide by its norm, or its length, in other words, and that gives you the unit vector in the direction of increasing r. Right? Phi hat is defined to be the unit vector that points in the direction we move when phi increases with r fixed. I should have put the unit vector in front of this because it has to be unit length. So here I have phi hat drawn in the picture. So remember, in trigonometry, the convention is the counterclockwise direction is considered the positive direction for angles. So phi hat points in the positive direction, the direction where phi increases with r fixed. Okay. And notice that these two vectors are orthogonal. Okay. Here I have a note: r hat and phi hat change with r, which makes taking their derivatives much more complicated than for Cartesian coordinates, because they're functions of time, right? If r changes with time, then so do r hat and phi hat. So it makes the formulas a lot more complicated. All right. In particular, it makes Newton's second law a lot more complicated. We'll get to that in a minute. All right, but like I said, r hat and phi hat are orthogonal, so we can use them as a basis for r squared, the Cartesian plane, or the polar plane. And so any vector can be expanded in terms of them. For example, we want to be able to expand the force, the net force on an object F, and we can do that because r hat and phi hat, like I said, they're orthogonal. Um, they are linearly independent. So F, so the net force on an object F is given by Fr, which is the r hat is the radial component of the force. So Fr r hat plus F phi hat. So F phi is the tangential component to the um, to the for the net force. Okay, the position, I can't speak for some reason. The position vector has a simple expansion in polar coordinates. It's given by r equals r hat, where this r without the vector notation on top means the length of r. So you can think of it as like having being the vector r, but with the double bars around it, right? It's just its length. Okay, however, drdt, like we mentioned before, drdt and the second derivative of r with respect to time are more complicated. So to find Newton's second law in polar coordinates, we need to find those two things. So I'll write down the derivation here on the following pages. So if we have two time periods that are not, instants in time that are not equal, t1, t2, and let's say that the angle for at t1 and t2 is different, then the position vector will be different as well. So here, if the little angle is, actually, let me get my pen so I can write on this. So over here, this angle is delta phi, right? That's delta phi is phi of t2 minus phi of t1. It's a small change in the angle. Then we have two different unit vectors, right? They point in different direction. Different directions. So we have r hat t1 and we have r hat t2. And then just to get a better grasp on the geometry, if we put these two vectors base to base, we get this triangle down here. And if you look at the difference between the two unit vectors there, this is r1, r hat t1. Just erase the subscript here. So this is r hat t2 rather, minus r hat t1. Right, that's this vector here. Okay, the length of that vector is approximately equal to the length of arc that I have drawn here in green, which, if you remember from pre-calculus or trigonometry, that's equal to r times theta. R in this case is the length of the unit vector r hat, which is 1. So actually, this thing is equal to 1 times the angle here, which is delta phi. So this whole thing simplifies to delta phi. Well, and I'll show you why we need that in a second. Let me just clear the picture here. Okay, so going down to the derivation. So here for delta r, which remember is this expression, that's equal to this. But that is approximately equal to, by this geometric fact here, is approximately equal to the length of r hat times delta phi times phi hat. Okay, which, like we said, simplifies to give you delta phi times phi hat. And delta phi you can approximate with phi dot, which is the time derivative of phi, times delta t, that's just the differential, times phi hat. And then we can, let me just erase this real quick. And then move this down. Oops. Oh, I gotta erase all this. Hang on. Can I just clear the screen? Yeah, okay. All right, so looking over here, delta r hat is equal to this, which I said is equal to this, is equal to this, is equal to this. We can divide both sides by delta t, which gives you the ratio delta r hat over delta t, and then take the limit as delta t goes to 0, and that gives us d. Sorry, there should be a d r hat here. Gives us dr hat over dt, which is equal to the time derivative of phi times the unit vector phi hat. Okay, so now we have the derivative for dr hat, and we can now go and derive the derivative for d phi hat. Where's the? Sorry, this should have been a hat over here. All right, let me scroll down. So we can use a similar, geometric argument for finding what the time derivative of phi hat is. And actually, I think I forgot d hat, or I forgot phi hat over here as well. This should be phi hat over here. Okay, so using a similar argument, again, just going up here. This is phi hat t1, this is phi hat t2. If you put them together with their bases over here, you get a triangle. And the sides of the triangle here are both length 1 because phi hat has length 1. It's right at it's unit length. And the vector delta phi hat, which is this vector over here, is approximately equal to the arc length that I have drawn here in green. Which is, again, by trigonometry, s equals r theta, which is equal to the norm of phi hat times norm of phi hat times, sorry, this should have been, times phi hat. Yeah, sorry. This is the angle, right? Phi hat. So s, this is r, and this is theta, okay? Okay, and then again, using a similar argument as above, delta phi hat is equal to the difference phi t2 minus phi hat t1, which is equal to this by what I said above. But notice that it's multiplied by negative r hat, just going back up to the picture so you can see. So over here, notice that r hat would point this way. This points in the opposite direction. So actually, you multiply by negative r hat instead of r hat here. And then when you simplify that, you get negative the time derivative of phi times delta t times r hat. And then again, divide by r hat, and you get, divide by divide by delta t, and take the limit as delta t goes to 0, and you get the derivative. So that's it's equal to negative phi dot times r hat. That's d phi hat over dt. All right, now we're ready to find the derivatives of the position vector, and then we can figure out Newton's law. And actually, this should be an arrow, not a hat symbol. Let me see. Actually, let me see if I can fix that a little bit more. Just so it's not confusing. All right, so this should be an arrow. This should be an arrow. Okay, so that the first time derivative of the position vector with respect to time is given by the derivative of r times r hat, right? Remember we had that simple representation for the position vector in polar coordinates. And that's just using the product rule that's equal to r dot times r hat plus r times d r hat dt. And we can plug in our formulas that we just derived up above to get what the formula is. So it's r dot times r hat plus r phi dot times phi hat. That gives us the first derivative. And then we can take the second derivative with respect to time. And again, just use our formulas. All right, so here if I want to find the second derivative with respect to time, differentiate the vector we just found, which gives you the next line. So you get r double dot r hat plus r dot d r hat dt. That's the derivative of this using the product rule. Plus, and then here you have to use the product rule to differentiate this, and then the formula to differentiate that we just derived up above. So you get r dot phi hat, r dot phi dot plus r phi double dot times phi hat plus r phi dot times d phi hat dt. All right, and then we can simplify everything there, combine like terms and whatnot, and you get this expression over here for d r dt. That's the vector form for the, sorry, this should be squared, second derivative rather. All right, so that's the polar representation for the second derivative of position in polar coordinates. All right, and each of these pieces has a special meaning, physical meaning, which he explains in the book. So here, each of the parts are described here. The part negative r phi dot squared, which is, let me change the color of my marker here. That's this part. Notice this is part of the component in the radial direction. This represents the inward centripetal acceleration. So, if you're moving in like a curved path, you have some component accelerating you towards the center of the circle with that, that curvature, whatever. Then the next part, r phi double dot, which is this part here. Notice this is in the tangential direction. That's the tangential acceleration. R double dot should be obvious. That's the radial acceleration. That's this part here. And then 2 r dot phi dot is more obscure. That's called the Coriolis acceleration. And he says, don't worry about it right now. We'll discuss this more in more detail in chapter 7. So we'll have to wait for chapter 7 to see, I guess, to explore that term. But until that time, we do have to know how to use it. So. Okay, so taken together, Newton's second law, F equals ma in polar coordinates, becomes this vector equation here. All right, and then we could just equate the respective components. You have to distribute that m, so it should have an m here. I'll just write it like this. So then this would be the component in the phi direction. So that gives you a system of differential equations that we have written down here. Notice that this is a very much more complicated looking system of differential equations than for Cartesian coordinates. Most notably, notice you get some nonlinear terms, which can make things a bit nasty. So, where's the eraser? Okay, and then he makes a note here. He says, note, Lagrangian mechanics handles non-rectangular coordinates as easily as rectangular coordinates, which is one of the reasons, I guess, why Lagrangian mechanics is so useful. And we're going to go over Lagrangian mechanics when we get to chapter 7. All right, so I'm excited for that whenever that happens. I know it's taken me quite a while to get through even chapter 1, but we should get to that at some point. At least this year, hopefully within a few months. But anyway, he ends the section 1.7 with an example where using polar coordinates is better than using Cartesian coordinates. So let me just read out the example. I'll explain, his solution, and then the next video I'll do the exercises for the section. So an oscillating skateboard. Oh, sorry. That's the title of the example. So an oscillating skateboard. A half pipe at a skateboard park consists of a concrete trough with a semicircular cross section of radius r equals 5 meters, as shown in the figure, which I've drawn on the next page. I hold a frictionless skateboard on the side of the trough, pointing down towards the bottom, and release it. Discuss the subsequent motion using Newton's second law. How long will it take to come back to the point of release? All right, so this is the picture. So we have a a skateboard rolling down the half pipe here, and we want to write down Newton's second law for that. This problem is best described using polar coordinates because the motion of the skateboard is completely a function of the angle phi. Because the radius of this half pipe is fixed, right? It's constant. It's always equal to capital R. So the motion of the skateboard is completely determined by the angle phi. Right, so we can write down the forces on the skateboard. They're just the normal force and the force due to gravity. So here in the radial direction, these are the forces. In the tangential direction, these are the forces based on the diagram that I have drawn here. Right. One thing to note is that this is not zero because it's circular motion. The normal force does have a has a component that's not just in this direction, right? There should be an accelerate. Sorry, there should be a force pointing in such a way that how do I say this? You have to have that centripetal force, right? That has to go this way, right? In order for the position vector to change direction. So this actually is not zero. It should be some negative quantity. This should be less than zero, which means that this component will be bigger than this component. But like I said, well, I didn't say this, but he says in the problem that that's actually not going to be an issue, and we'll see why in a second. Right, so Newton's second law, just writing it out, the one that we derived before, Fr is equal to this expression here, which we can simplify because we know that R is fixed. So that means that the second derivative of R is zero, right? Because R is a constant. So this simplifies to give you this expression here, which is when I plug in capital R, you get this expression. R is a constant. And this is the centripetal acceleration times the mass. So that's what that component represents. And then F phi is equal to this, which is, oh, sorry, the force is equal. Wait, did I not write the force down? I guess I forgot to write this force here. Sorry, this should have been replaced by, let me move this up. By that expression there, I must have forgotten to write it. So this is the force in the phi direction. And then again, just writing down Newton's, the formula that we used for Newton's second law. Notice that this derivative is zero because R is constant. So this simplifies to give you this. And then when you plug in capital R in for little r, you get this expression here. So we get a second order differential equation for this one. Right, just scrolling down. Now going back to the part with the normal force, we this differential equation that we get here. So negative Rm phi dot squared equals mg cosine phi minus n. The book says we can actually ignore this part because we're actually not interested in the normal force. In fact, since the motion of the skateboard is along a circle, we know that the radial direction will always be fixed. So we can, in other words, the motion of the skateboard is completely determined by phi. So we can actually just focus on this part here, which comes, this part here, this differential here. What I did notice, I just canceled the m's just to get a simpler expression. And then I solved for phi double dot, which is the second derivative of phi with respect to time. So we get this differential equation here, which looks innocuous enough, but actually it turns out that this is a really non-trivial differential equation. The solution is something called the Jacobi elliptic function, which you can't actually express in terms of elementary functions, but we can get an approximate solution um, to the differential equation by using this small angle formula here. If the angle is tiny, if it's close to 0, then if you remember from Calc 1, that means that sine of the angle is approximately equal to the angle. So we can replace, as long as, like I said, as long as the angle is small, we can replace sine phi with phi. And then this is just an ordinary linear second order differential equation. It's even easier because it's homogeneous. So you can solve that by finding the general solution, which if you remember your differential equations, in this case is given by this expression here. And then, okay, and then we can figure out what the constants have to be. So phi of 0 is equal to b, like when you plug 0 in for t here and for t here. Sine of 0 is 0, so that term goes away. Cosine of 0 is 1, so you're just left with b. So phi of 0 is b, which we'll call the initial, that's like the initial position, I guess, the initial angle, phi 0. And then also, since we're releasing the skateboard from rest, that means that the velocity, the initial velocity will be 0. So phi dot 0 is, again, when you plug 0 in for the derivative, you take the derivative of this, you get maybe I'll write it on top here. Phi dot t is equal to a times square root g over r cosine square root g over r t minus b square root g over r sine square root g over r t. That's the derivative. And if you plug 0 in for t, this goes to 0, and you're just left with the coefficient here because cosine of 0 is 1. So we get this expression here. And like I said, we're assuming that we're releasing the skateboard from rest. So in other words, the initial velocity is 0. So that means that a has to be equal to 0. So we get the position function for the skateboard at time t, which is given by this expression here. So phi 0, which is the starting position, times cosine square root g over r, which is the frequency times t, and that means that the skateboard repeats its positions for with period tau equals 2 pi square root r over g, right? Because remember, cosine has period 2 pi. So that gives you the I think that's what they asked us to do. They've wanted us to find the position of the skateboard at time t, and they wanted us to say when it would repeat its initial position, and this will be the time it takes for it to do that. Okay, so that's the example that he ends the section with. Just make sure, did I have anything else written here? Oh yeah, and then he gave us that the radius was 5 meters, so you can actually figure out what the number is. It's 4.5 seconds. So that's the end of the section, and actually the end of the chapter. The only thing that we have left to do in chapter 1 is the exercises for section 1.7, which sorry, my nose is getting stuffed here. Which is what I'll do in the next video. So keep an eye out for that. Let me just stop the screen share. Keep an eye out for that, and I hope to get another at least 1 or 2 videos out this week. Again, I apologize for my slow schedule here, but it's because I'm super busy at work. But I'm hoping that my schedule is going to die down a little bit, within the next few weeks, because the spring semester has started. So Anyway, that's neither here nor there. Look out for a few new videos this week. And until that time, keep learning, everybody, and I'll see you in the next one.